So, we continue from where we left on the texturing of spun yarns, and to recall, we learned that the twist texturing of spun yarns can be done by some of the following techniques. Sheath core, which means that in the core you have an elastomeric yarn and the sheath is any other yarn which is spun onto that. Or we can take, in the case of cellulosic, you can introduce thermoplasticity and use the thermomechanical means. We can do simply by solvents, decrystallization, recrystallization. In the case of any fiber for that matter, cellulosic material as well. For cellulosic materials, you can change the surface by coating a thermoplastic polymer, which could be done by interfacial polymerization, and also covalent cross-linking, which today we will consider a little more in detail. So, we focus today on twist texturing of cellulosic spun yarn. So, we are concentrating on cellulose. Spun yarns, of course, is the general thing, and using covalent cross-linking. Among the many methods that we saw that were possible, that are possible. So, we are looking at covalent cross-linking. There was a time when cross-linking and various kind of cross-linking agents became very important, because we wanted to improve the crease recovery properties of cotton or viscose fiber fabrics. A lot of research was done on various agents. It is only after the advent of synthetic fibers coming into the market. Once they were in the market, then it appears that the crease recovery properties of thermoplastic fiber fabrics were much better. And so, some emphasis was reduced on the cross-linking agents, cross-linking process, which used to give wash and wear fabric or durable press fabrics, and so on and so forth. But of late, it has been noticed again that for the reasons that these fiber fabrics are biodegradable, and therefore, they become much more important than the synthetic fibers. And so, today again you will see a large number of cellulose based material, dress material, suiting, shirting material will be available, which says durable press, permanent press, and so on and so forth. And therefore, emphasis has come back on the cellulosic material and also the way you make them crease resistant, and that is done by this covalent cross-linking. So, the question was that why does it happen is because you are able to set some of the deformations or resist further deformation by putting intermolecular cross-links. So, theoretically they thought that, well, why not? We can do this process on cotton and viscose and produce a textured yarn. What it meant was that you are supposed to introduce cross-links, intermolecular cross-links within the fiber, so that one can get the twist, which is a deformation mechanism, set in a better manner. So, the general process would be, as we discussed last time also, instead of one single yarn, you will take 2 yarns and give them a ply twist, and then you do the setting and the detwisting past the neutral ply twist. What it means is that you have done X ply twist in Z direction. So, after setting you will give x plus delta x in the z direction. So, that in the final textured yarn, because there are only 2 yarns, they should not absolutely separate out a certain amount of twist, which is 2 to 3 turns per centimeter or less could be there. So, that the yarn actually behaves like one rather than 2 different yarns. So, it is a bundle which is important. So, people give slightly more than the retwist is slightly more than the twisting. So, that some twist, right. You remember even the multifilament yarns, we said that either twist or air entanglement may be required just to make sure that they just behave like one body. So, we also said that this process in some way, that is the cross-linking process, in some way represents thermo-chemo-mechanical texturing. So, you may be heating to get the reaction done, you are using a chemical. So, it is a chemo, and mechanical because you are still twisting and detwisting. So, whole process therefore, would relate to this type of a texturing process, thermo-chemo-mechanical texturing. So, setting, as we learned before also, there are 2 ways in which you do the setting: release of energy or freezing in. So, the cross-linking is in this category, where you are not releasing the energy, you are freezing. That means, after twisting, where the internal energy would rise because you are twisted, you have put the mechanical energy and you do not allow it to release. It stays there as it is, fixed, frozen in by additional covalent crosslinks. So, one important thing you must remember always is that you are not releasing the energy in this process. So, again setting is by freezing in principle by using various kinds of cross-linking agents. So, what are the cross-linking agents can be? A cross-linking agent, here remember we are talking about the one which will finally make a covalent bond. The minimum requirement will be that this is a molecule which has got some length or some segment which has got 2 functional groups, at least 2 functional groups. These functional groups are supposed to react with, let us say, cellulose, and so if they react at 2 points, so it makes a cross-link. So, you cannot obviously think of making a cross-link by using a monofunctional agent, right. It will only get like a reactive dye makes a one single link. So, it does not cross-link, but a bifunctional reactive dye can actually produce some cross-links as well, because it has 2 functional groups. Can these be multifunctional? Yes, it can be multifunctional. You can have more than 2 functional groups. People generally may not prefer in a situation where flexibility is the hallmark, because if you have trifunctional, hexafunctional compounds, they can make network, and so the body or this whole thing become rigid. Like you have phenol formaldehyde type of situations or melamine formaldehyde. Melamine formaldehyde is a multifunctional group, and it can make very rigid sheets like Malmaware, that you have unbreakable plastics, what you call them, thermoset material, but that will not be good for anything called texturing. You need flexibility, stretch, bulk. So, we should not use multifunctional agents as a cross-linking agent. So, some of the groups which can easily react with, let us say, cellulose, we are not discussing cellulose, right. We are discussing how to texturize cellulose, spun yarns. So, some of the reactive groups which can react with cellulose can be listed like this: epoxy, right. Epoxy groups, you must have seen a product called araldite, right. So, if you have, they are epoxy based resins, they can cross link. They can make hard things also, but if you ensure that only reactions are limited and not in a 3-dimensional things, you will get flexible things also. Some these epoxies may look like this. So, you may have R, and you can have another epoxy. So, it's a tri-membered ring, you know. If you have heard of Baer strain theory, they are very reactive, they are more unstable. It is because 3-membered rings are generally very unstable and they are therefore reactive, they can react. So, what will happen obviously is this 3-membered ring is going to break up and theoretically can react with cellulose. If there is a cellulose somewhere, which we can represent as cellulose and one hydroxyl group, then so this type of a link can be formed, and this somehow leaves the hydroxyl group behind as well. So, in one way one can say, well, it blocks one of the hydroxyl groups of cellulose, but simultaneously creates another hydroxyl group. So, hydrophilicity may not be affected, right. So, overall hydroxyl groups could be there. So, the other similar type of a group are in the series which we call as epimines. Epimines are again 3-membered ring which are nitrogenous compounds. Here again it is a 3-membered ring and therefore, it can break under, like epoxy generally would be more reactive in alkaline medium. Epimines can react in acidic medium, and one will be able to react and get some link of this type. If cellulose is reacted, and of course, on this side also something similar would be there. So, you can get a cross link which in a way you can consider as the ether link. So, this is a ether link. This can be also generated. So, one can produce crosslinks in this manner. The other interesting group which have been very effective and commercially, actually the textile people use them, relate to a class of called the N-methylol compounds. So, you have again a nitrogenous compound. So, this is the N-methylol group. So, you can attach with any R and have two such groups, then they can also react with cellulose to make crosslinks. Acid chlorides are also, if you remember, sometimes we talked about very reactive compounds which can go for interfacial polymerization also with any type of acid, alcohols and so on and so forth. They can also react, but people have tried isocyanates also. So, one can have type of groups which can also make crosslinks. They are very reactive compounds and they can form. There are other compounds also which have been used to produce crosslinks, but as I mentioned, this group has been commercially more successful because the conditions for generating crosslinks suit a normal textile process where the time and temperatures are in your ranges where you work. Epoxies, epimines, etc. probably will be working through liquids and solutions. You may or may not be very happy doing a cross-linking solution, it will take more time. Acids and isocyanates, acid chlorides, isocyanates are dangerous in some sense, you have got to be very careful while you are using them, but they are generally relatively much more safer. Of course, there are other than these compounds also people have used for cross-linking purposes. So, N-methylol compounds. The first such compound which somebody said produced was from a urea. So, you have simple urea. So, you have dimethylol urea, which meant a molecule like this. This is urea with 2, but if you add CH2 OH here and a CH2, so compounds like this were generated which were acid catalyzed. Another series of compound which came we call the DMEU, which is dimethylol ethylene urea. Another compound which again became quite commercial success was called the DMDHEU, which is dimethyl dihydroxy ethylene urea. The compound something like that. So, this compound and the previous compound, the difference is this is linear and this is a cyclic compound. So, this by itself is a 5-membered ring, so relatively more stable, it does not break. The reactions are going to be taking place with these N-methylol is because nitrogen's got a lot of lone pair, and therefore it is easy for reactions to take place with the hydroxyl groups of cellulose. Well, similarly, people went on to say instead of ethylene you have a propylene urea, a propylene hydroxide urea. Not only that, instead of methylol they talked of compound which are NCS2 instead of OH, some other alkyl group. So, alkylol and alkylol compounds could also have been used. It is basically to balance what they call as a reactivity versus stability. So, in some cases reactivity may be high, stability may not be so high. Stability means basically hydrolytic stability. All such materials after being applied will have to be, all textiles will be washed many times over. So, if the crosslink breaks, then obviously it is not effective. Hydrolytic stability is one which people like to work around. So, the general mechanism of reaction with cellulose, we are now looking at the N-methylol compound, which I said they became relatively more commercially successful compounds, and they are still. So, acid catalyzed, if you have a reaction something similar, so this proton acts and adds itself, and later in the reaction a water molecule goes. You get a carbonium ion which is reactive. This can react in the presence of cellulose to give something like this. A link, and in the process releases the proton back. Therefore, it is catalytic. So, you are not consuming the catalyst as such, it goes and comes back and you get the reaction. So, this is what in the meantime you obviously are removing one water molecule every time. So, there is a substitution reaction and again forming an ether link. Ether link is relatively more stable in alkaline conditions, and therefore, when you wash, you would have better hydrolytic stability compared to an ester link, because most our washings, our soap, detergents are alkaline, and so this can. So, the cyclic compounds became more popular than the linear compounds, because although the reactivity was reduced, but hydrolytic stability improved, and so a large number of them are going to be the cyclic compounds. And the linear compounds also had another problem, which means that if we look at urea, for example, formaldehyde, if this is the kind of reaction that happens. So, this part which has got a hydrogen on the nitrogen, this is called a labile hydrogen. In a cyclic compound, this labile hydrogen is not there. Labile hydrogen, nitrogen having lot of lone pair of electrons, so this can easily get replaced by, if you have a bleaching solution somewhere, it will become NCl instead of NH, and will keep coming out whenever you do ironing or any other thing, HCl can come out and then degrade yellow the fabric. So, this was called a chlorine retention problem. So, whenever you have a labile hydrogen on nitrogen, you may have a chlorine retention problem, and cyclic compound therefore do not have such issues, and so a good number of such agents therefore have been used. So, the cross-linking process is for setting, pad dry cure. This is the process which is used for the fabric, and if you have to use for texturizing also, the same process has to be used. Padding means you have a solution of a cross-linking agent and a catalyst also, and they have to be applied onto textiles. One of the easiest way of applying is padding, and then you dry and then a cure. Purpose of drying is to remove water, and purpose of curing is to generate a cross link. So, that means these things are going to be done at two different temperature ranges. This drying may be better less than 100 degrees centigrade. Aim is to remove water, and the curing obviously will be somewhere 120 to 150 degrees centigrade, where we expect in general a reaction may take place. So, do we wash? We have to wash. So, this is therefore different than the normal texturing process for thermomechanical texturing of thermoplastics, because in every reaction you can have unreacted compound, then you have added a catalyst, which obviously is just a catalyst for reaction. After that, it has no purpose to serve. So, you will be washing, drying. So, additional steps may have to be taken if you want to complete this setting process, and then you will do the detwisting. So, you have the twisting part, then the setting, which is a long process, which is messy in the sense that it has got liquid, water, drying, washing, all those kind of things, and then detwisting. So, if you do all those, then you are likely to get textured yarn. So, just some word about the catalysts for the same type of compound, which are the N-methylol compounds. So, acids can be used because they give proton. Mineral acids can be used, HCl, H2SO4 can be used, nitric acid people do not use, too strong. Organic acids like citric acid, glycolic acid, and such compounds can be used for catalysis purposes. The only thing is that they are active, obviously they are ready to give proton, and so some strength loss due to the acid itself can happen. And so people would like to not use the acids directly for catalysis, but use something else than catalysis, strength loss. I am sure you know the cellulose can be dissolved, or at least there is a test method in sulfuric acid. So, it means it can degrade. So, it has to be used as a catalyst, and when you go for higher temperatures also strength loss can occur. So, one may like to remember that whenever you do cross linking in a manner in which we have just described, the tenacity is going to reduce because of the acid. So, we call them acid losses. We are talking in terms of tenacity, we are not talking in terms of mass. So, cellulose is sensitive to acid. All ether links are sensitive to acid. Then temperature, we are saying curing temperature is going to be high. So, because of acid plus temperature, again the loss can take place. At room temperature, the difference, it will be different, and higher temperature, it is different. You see, when what happens is, when you dry, whatever concentration of acid that you have taken in the beginning on the fabric, as the water goes out, the concentration of acid keeps on increasing. So, acids can become concentrated on the substrate and then can do, but if they become concentrated only at the time When cross-linking is required, then they are participating in reaction. If it happens before, then it can, right. For example, if you do not use a cross-link agent, just have acid and temperature, you will get the loss higher than when you have a cross-linking agent. The cross-linking itself is supposed to bring some loss, but that depends on which fiber we are talking about, right. So, this is just by cross-linking. Even if there is no acid loss, if there is no loss due to temperature or high temperature, just by cross-linking you can get something like this, particularly in cotton you observe this. This is a hypothesis proposed by Rebenfield, and what it says is that if you have less cross-link density, if you keep on increasing cross-links, the tenacity of, let us say, the yarn or the fabric will increase. After a certain point it will start decreasing, and as they say, the cotton actually lies here. So, when you increase cross-link, so you are going in this direction, so you will lose just because of this. Its reverse happens when you decrease. When you decrease, let us say by wetting. So, hydrogen bonds, so this cross-link is not only chemical cross-link, is representing everything, intermolecular, all kinds of bondings. Like hydrogen bonds reduce, so the strength increases. So, we see the cotton strength in wet state is higher than the dry state. So, this is one. On the other hand, if you have viscose, which actually has a low crystallinity and so on and so forth, overall cross-link density is less. In this case, reverse happens, that if you do the increase the cross-linking, the strength can increase if these two have been controlled. If you wet, the wet strength of viscose is low, right. So, you can obviously have this. In addition, the texturing. So, what is texturing doing? It is twisting first. It is not like the fabric or a fiber or a yarn is in a relaxed state. It is actually not in a relaxed state. You are twisted, and you are going to be cross-linking a twisted yarn, because that is what the texturing has to be used for. This is how the texturing will be done. So, what it means is a material has been subjected to stresses, and the stresses are being stored in. And so, this material will become weaker in that sense also. Who likes to be under stress? Any material under stress can fracture, crack, and so tenacity after cross-linking, or let us say after texturing by this method, is likely to be less, and it has nothing to do with what we were talking about was disorientation. That is another thing. Here intermolecular changes are not taking place, they are as it is, but whatever you are doing is also not very helpful as far as tenacity is concerned. So, effort therefore is what to do. So, you can reduce the loss due to the acidic environment or reduce the temperature of cross-linking, and therefore, you can do, but cross-linking by itself, whatever it does, it will do. You may not be able to change that part. So, instead of acids, people suggested using metal salt. Metal salt becomes effective because of the metal. The higher is the oxidation number of the metal, higher is its activity. So, people do not use aluminum chloride generally because it is very active, and you may have more degradation because of this activity. But settling down, people settle down at magnesium chloride, zinc chloride, etc. Zinc is relatively a heavier metal, so magnesium is not so heavy metal. This is one of those popular catalysts which has been used, and it works in the same manner as the proton based system. Say a metal with whatever oxidation number that you have. If you have more, it will work like that. Metal hydroxide may come out, and you get again a carbonium ion. After that is the same reaction. Get the proton back. So, they also become considered to be more active, because this MOH can react with the generated proton and can produce H2O plus metal ion, which can go like this, or the proton itself can catalyze. So, therefore, the probability becomes of its effectiveness is good, but it is not more degrading, because this process starts only after a certain temperature. It does not, you can store it at room temperature, not much thing will happen. But if you store sulfuric acid based fabric at room temperature, things will keep happening at room temperature as well. So, that way it reduces the strength loss and still effective. Similar compound like latent acids, which ammonium salts, they at room temperature are not very effective, but at higher temperature ammonia will be liberated and suddenly they will become effective. So, people also tried to use metal salts along with organic acids. Organic acid by themselves catalyze, metal salts can catalyze, but when they are present together, then a complex can be formed where the metal ion is handled by the organic acid, or organic acid remain complexed along with the metal, and at a later stage both of them are available. And what people have seen with this type of thing is the temperature of the curing can be reduced from 150 degrees to 120 degrees, 110 degrees, which means less loss in strength. People are concerned about the loss in strength. Loss is one part of it, but if it becomes yellow also, then you see it. So, you may not like to do that. Another very interesting class of catalyst is called a phase separation catalyst. Phase separation. That means during this process of curing, the catalyst separates in two phases, and the pH of the solution or wherever it is, obviously as you do the drying, if you do drying, that is the moisture is going up, the concentration keeps on increasing. So, pH goes down, but at some point it falls rapidly, and that is the point which is a critical concentration where phase separates, and so activity starts increasing. And so, this again to reduce the loss due to acids. One of the example of phase separation catalyst is hydrogen phosphates. So, magnesium hydrogen phosphate, aluminum hydrogen phosphate, they are called the phase separation catalyst. It's because of the phosphoric acid being such a nice acid that hydrogen can come from here, can come from here, can come from here as the phosphoric acid is concerned. But when you react with, let us say, magnesium, ammonium and so on and so forth, these activities are subdued. So, if you have a magnesium dihydrogen phosphate, which is an example given. So, in a solution where this has been dissolved, one can have hydrogen ion, which is interesting. You can have magnesium ion, which is a metal ion, so which is interesting. You may have hydrogen phosphate ion, or you may have a dihydrogen phosphate ion. All of them are present depending upon dissociation that keeps on happening at any given point of time. It so happens that means you have a magnesium hydrogen phosphate as well as magnesium dihydrogen phosphate available in the solution as far as dissociation is concerned. And as you dry, at some stage the solubility of the magnesium hydrogen phosphate is less. In water it precipitates and the other one becomes more active. In the beginning most of this is because of this, and so it works like a weak acid. The moment the other compound, which is magnesium hydrogen phosphate, which is from here, which is this has a low solubility, it precipitates and therefore equilibrium shifts and more of protons are produced, and we will get a phase separated and a pH change which will look something like this. This type of compound has been also found to be very good as far as less stable, less degradation, and is otherwise quite stable to the what we call as a temperatures. If it was a ammonium phosphate or dihydrogen phosphate, ammonia would get liberated. Magnesium does not get liberated in that manner, and one would see good cross-linking. So, we just see some of the work that has been done in this. So, the process in this experiment was done as a ply twist, set, detwist, pass the neutral ply. So, setting was done by pat dry cure, wash dry method. I am just trying to tell you why we do drying, because drying means low temperature removal of water. You can dry at high temperature also, but that is what is the standard one. Some resin, which could be DMDH or any other resin, some softener, because invariably people have found that some stiffness occurs, so softener will do the reverse of it. A catalyst, whatever catalyst that you may like to use, some wetting agents, so everything gets surface tension reduced and so on and so forth. That type of a thing can is a starting point. So, you do the twist and the twisted yarn is padded, right, and then dried, cured, washed before detwisting. This is typical. Change the resin, change the catalyst, concentration, etc., everything will change. So, any kind of a wash and wear treatment, something like this one would see. So, then comes the curing conditions. Now, we are just trying to emphasize based our need of texturing also. So, normal curing conditions after drying could be, let us say, 120 to 150 degrees centigrade. Now, here general time required could be 4 minutes to 5 minutes or 3 minutes to 5 minutes, while we were discussing times of the order of 0.1, 0.2, 0.3 seconds. Now, you are talking about minutes, right. Time here is in minutes. So, you may have 3 to 5 minutes as a time. So, the people thought if we have this, therefore, it has to be a batch process, then nothing else can be done, and it will be more and more unattractive. So, people also have what we call as a high temperature curing. High temperature curing means that you can go beyond 200 degrees centigrade. Considering the time temperature issues, that means at high temperature time would be reduced. If the time comes in seconds, then there is a possibility that you may actually have a continuous process also. In a minutes, one can think of continuous process, but it's like a stenter, doing all kinds of things at a long size. Look at a texturing machine, one simple heater, and going through the whole thing versus a whole stenter business which people use for the textile fabric. So high temperature curing is actually, believe this is pad dry cure. This also is pad dry cure, but at higher temperatures. There is another term which is called a flash curing, which pad cure. Their aim was that, well, if you are going to high temperature, drying will also take place, right. But people would prefer drying step in between, because if a higher temperature, rate of drying is very high. In some sense it is good, but because of that high rate, some of the chemicals can migrate from inside to the surface as they are coming. So, migration in the wrong direction. So, you have a non-uniform cross-linking. If you have a non-uniform cross-linking, you can understand what will happen to the properties. So, cross-linking is a bulk change, property change in bulk, like thermomechanical also change in the whole bulk. So, you can't have only surface being treated or treated more than the rest. So, people may not prefer flash curing as such, but you may go for high temperature curing. That means you dry initially at a low temperature and then cure at a high temperature, that you can go faster. So, one example which I am just listing here is some of the viscose yarn, which was some 18 tex 7.9 twist per centimeter, twisted in Z direction. This yarn was doubled and twisted to some twist level like 18.5 twist per centimeter, again in Z direction. This is an important thing, So, even if you do ply twist, you are not supposed to do the ply in the reverse direction. You may do a bad job. Some of the yarns may start opening up. So, Z on Z, right. So, you do Z on Z. Obviously, when you will do the reverse twisting, it will be in S direction, that is it. So, you pad, dry, high temperature curing, that means you are going for padding, drying and higher temperature curing. Washing and drying, untwist, pass the ply and then see some of the properties. So, some result here, curing temperature 210, time was 2.5 seconds, 2.5 seconds. The catalyst here is magnesium diiron phosphate, which means this is phase separation catalyst, all right. Some concentration, measurement of nitrogen has been done, because when the cross-linking agent gets added, you do have a nitrogen also getting added. So, you can measure nitrogen. So, some strength loss you can see from a control 120 to 109. Extension at break also reduces and some crimpity has been obtained. That means, this material is now a textured yarn, which obviously has got helical structure, and you can do stretch and bulk both. So, if you have this process coming up to this level, one can use a blended yarn also, like polyester viscose, polyester cotton. If times are less, then you may think of phosphorus texturing. If possible, you can think of texturing and dyeing together, because there is a process called Procion resin process, where in acidic medium the reactive dyes can react through the resin and dye also. So, one can think of, you go for a high temperature curing, you can go for a mixture of dye and resin, and theoretically you can do continuous dyeing and texturing. So, one example here is where less polyester has been taken, more viscose, but if you change the percentage of polyester, obviously thermomechanical setting of the polyester will help. If it is more of viscose, you have to have more of cross-linking agent. So, similarly done, 210 time 2.5, same catalyst, it is a blend. So, you can do texturing as well. So, what we learnt is that cross-linking can be used to texturize cellulosic spun yarns. Effective selection of resin and catalyst can reduce curing time. Blended yarn can be texturized. Continuous texturing can also be done. So, some conclusion from that point of view. Thank you.